In the vastness of the universe, everything we see, every star, every planet, and every galaxy is part of a larger structure. But some structures are so immense, so quietly dominant, that they reshape the very fabric of cosmic history. These aren't just single galaxies, or even small collections of a few. They are galaxy clusters, the silent giants of the universe. Imagine this: each of these colossal structures can contain thousands of individual galaxies, all bound together by the relentless pull of gravity across tens of millions of light years. To put that into perspective, they are the largest, most massive structures ever held together by gravity-enormous islands of matter drifting through the endless cosmic sea. And yet, for all their power, most of it is completely invisible. Their true mass isn't in the stars we see, it's hidden. It lurks in vast, mysterious halos of dark matter and in clouds of plasma so hot they glow with X-rays. We can only detect their immense presence indirectly, by observing how their gravity distorts radiation and bends light from distant objects behind them. As light from far-off galaxies travels towards us, passing through a cluster, the cluster's immense gravity acts like a giant cosmic magnifying glass. This phenomenon, known as gravitational lensing, warps the fabric of space-time itself, causing the light to bend and creating beautiful, distorted arcs and multiple images of the background galaxies. It's a stunning visual confirmation of Einstein's theory of general relativity, and it allows us to see the invisible dark matter that holds these clusters together. Without gravitational lensing, the true scale and mass of these giants would remain a complete mystery to us. But galaxy clusters are so much more than just massive collections of galaxies and dark matter. They are dynamic, violent, and incredibly active environments. Think of them as cosmic laboratories where the most extreme processes in the universe unfold. Inside these clusters, galaxies are constantly moving, interacting, and colliding. When two galaxies merge, it's a spectacular event that can last for hundreds of millions of years. Stars are thrown into new orbits. Gas clouds are compressed, triggering massive bursts of new star formation, and supermassive black holes at their centers can roar to life, feasting on the influx of new material. These galactic collisions and mergers are the primary way galaxies evolve. Over cosmic time, smaller galaxies are stripped of their gas and stars as they fall into the dense core of a cluster, a process called galactic cannibalism. This is how the largest galaxies in the universe, known as central dominant or CD galaxies, are formed. They sit at the heart of clusters, having grown to enormous sizes by consuming their smaller neighbors. Studying these interactions gives us a direct window into how galaxies like our own Milky Way have changed and grown over billions of years. It's a story of creation and destruction, written on the grandest of scales. Over the 13.8 billion years since the Big Bang, these clusters have grown from tiny, faint ripples of density in the early universe into the titanic superstructures we observe today. They are not static objects. They are still growing, pulling in more galaxies and gas from the cosmic web, the vast network of filaments that connects all matter in the universe. By studying how the number and size of clusters have changed over time, cosmologists can trace the history of cosmic expansion and even learn about the mysterious force driving it. Dark energy. Galaxy clusters. These silent giants hold the keys to understanding not just the past, but the ultimate fate of everything we know. So, the next time you look up at the night sky, remember that the faint glimmers of light are part of a much larger, grander story. A story of silent giants, of hidden power, and of structures so vast they have quietly sculpted the cosmos since the beginning of time. They are the galaxy clusters, and they remind us just how much of the universe is still waiting to be discovered.
Ever wonder how the universe built its greatest cities? Not cities of concrete and steel, but magnificent metropolises of stars, gas, and dark matter called galaxy clusters. To understand them, we need to rewind the clock all the way back to the beginning. Imagine a universe without a single star or galaxy. Just moments after the Big Bang, all that existed was a dense, searingly hot soup of particles, a chaotic ocean of energy. But as this cosmic soup expanded and cooled, a quiet force began to take charge. Gravity. It started small. Tiny, almost unnoticeable wobbles in the density of this early universe. Some spots had just a little more stuff than others. Over millions of years, gravity latched onto these tiny differences and amplified them. The rich got richer. These denser regions pulled in more and more surrounding gas and invisible dark matter. From this cosmic tug-of-war, a breathtaking structure emerged. The cosmic web. Picture a vast, glowing network of filaments stretching across billions of light years, like a spider's web woven from pure starlight. These filaments are cosmic superhighways, made of galaxies, dark matter, and hot gas, all flowing like rivers through the void. And at the intersections where these cosmic rivers meet, the universe's grandest structures were born. Galaxy clusters. So, how did this blueprint for the cosmos actually get built? It all comes down to that one fundamental force. Gravity. It's the architect of everything, from the smallest stars to the largest clusters. In the early universe, most of the matter wasn't the stuff we can see, it was dark matter. This mysterious, invisible substance acted as the scaffolding for the universe. It clumped together first, forming dense knots called halos. Think of these halos as gravitational wells, deep pits that ordinary matter, the gas that would one day form stars and galaxies, couldn't resist falling into. These dark matter halos were constantly merging, colliding, and growing, getting bigger and bigger. Inside them, gas cooled, condensed, and ignited, forming the very first galaxies. But the story didn't end there. Over billions of years, this process scaled up. Individual galaxies drawn by mutual gravity began to fall toward each other, forming small groups. These groups then merged to form clusters, and clusters in turn merged to form even larger superclusters. It's a process called hierarchical assembly, a slow, majestic cosmic dance of accretion and merger that built the large-scale structure of the universe we see today. That's why when we look out at the cosmos on the largest scales, we don't see a random sprinkle of galaxies. We see this incredible cosmic web, with galaxy clusters anchoring its brightest and most massive nodes. Each one is like a cosmic fossil, a snapshot of how the universe has grown and evolved over 13.8 billion years. Now, let's talk about the incredible forces at play inside one of these clusters. The gravitational pull is absolutely immense. Individual galaxies whip around the cluster center at mind-boggling speeds, up to 1,000 kilometers per second. To put that in perspective, that's fast enough to travel from New York to Los Angeles in about 4 seconds. At those speeds, any galaxy should have been flung out into deep space long ago. This very paradox stumped early astronomers like Fritz Zwicky back in the 1930s. when he studied the Coma Cluster. He realized the galaxies were moving way too fast to be held together by the gravity of the stars and gas he could see. There had to be something else there, something massive and invisible. This was one of the very first pieces of evidence for what we now call dark matter. So, the birth of galaxy clusters didn't just teach us how the universe builds structure. It revealed that most of the cosmos is hidden from our sight. But clusters aren't just galaxies and dark matter. They are also filled with an enormous ocean of hot, ionized gas, known as the intracluster medium. This gas, which fills the vast spaces between the galaxies, is heated to temperatures of tens of millions of degrees by the cluster's crushing gravity. It's so hot that it glows brilliantly in X-rays, creating a luminous halo that's completely invisible to our eyes, but shines brightly for space telescopes. And here's the kicker. This hot gas contains more ordinary, baryonic matter than all the stars in all the cluster's galaxies combined. It's a blazing reminder that the universe we see, the stars, its planets and beautiful nebulae, just the tip of the cosmic iceberg. Over time, these clusters evolved into dynamic ecosystems. They aren't just peaceful collections of galaxies. They are active, sometimes violent environments, where galaxies are constantly interacting and changing. For example, a galaxy moving through the cluster can have its gas brutally stripped away by a process called ram pressure stripping, like a cosmic wind blowing through it. This can shut down star formation, leaving the galaxy to fade into a red and dead relic. Galaxies and clusters are also more likely to collide and merge. These cosmic pileups can trigger spectacular bursts of star formation, creating brilliant starburst galaxies. But eventually, the harsh cluster environment tends to quench this activity. So every spiral galaxy that gets reshaped into an elliptical one, every burst of new stars that fades away, tells a story of the powerful physics at work inside a galaxy cluster. They are constantly shaping the lives and deaths of the galaxies within them. It's hard to wrap your head around just how big these things are. A typical galaxy cluster can span 10 million light-years, cross and weigh about a quadrillion times the mass of our Sun. That's a 1 with 15 zeros after it. The famous Coma Cluster, located about 320 million light-years away, contains over 1,000 galaxies. And even that is just a small part of something bigger. Our own Milky Way is part of the Laniakea supercluster, a colossal gravitational basin containing hundreds of thousands of galaxies. These structures are the true gravitational anchors of the cosmos, dictating the flow of galaxies across unimaginable distances. So when we study galaxy clusters, we're doing more than just looking at distant objects. We are watching the fundamental forces of the universe play out on the grandest possible stage. The intricate dance between dark matter, visible matter, and even dark energy is on full display. This makes clusters perfect cosmic laboratories. By studying them, scientists can measure the ratio of dark to visible matter, investigate the physics of superheated plasma, and even observe the influence of dark energy on the expansion of the universe. The way clusters move and grow helps us test the very foundations of cosmology and allows us to glimpse the ultimate fate of the universe itself. From the first ripples in the newborn universe to the colossal cosmic cities we see today, the story of galaxy clusters is the story of gravity's creative power. They are the masterworks of the cosmos, the silent architects of its grand design, holding the secrets to both its past and its future. Look up at the night sky. You see stars, maybe a planet, perhaps the faint glow of the Milky Way, but what you're seeing is just the very beginning, the merest hint of the true scale of the cosmos. Out there, in the deep, dark voids between the constellations, gravity has spent billions of years sculpting structures so vast they defy imagination. These are the cities of the universe, the largest gravitationally bound objects in existence, galaxy clusters. Each one is a metropolis of hundreds, even thousands of galaxies, all swirling together in a single, titanic embrace. But these clusters are more than just pretty collections of lights. They are the fundamental architecture of the cosmos, the scaffolding upon which the universe's grand design is built. They hold the secrets to the universe's most profound mysteries, from the invisible matter that shapes reality to the very fate of the cosmos itself. Today we are journeying into the heart of these cosmic giants to uncover the stories they tell, stories of gravity's ultimate triumph, of epic collisions that reveal the unseen, and of the hidden power that governs everything. Our story begins about 320 million light-years away, in the constellation Coma Berenices. Here lies one of the most famous and densely packed regions of the nearby universe, the Coma Cluster. Through a powerful telescope, it appears as a delicate smudge, a gentle concentration of faint lights. But in 1933, to an astronomer named Fritz Zwicky, this cluster became the site of a revolutionary discovery. Zwicky was measuring how fast the galaxies within the Coma Cluster were moving, and what he found was completely baffling. The galaxies were zipping around at incredible speeds, so fast, in fact, that the cluster's visible mass couldn't possibly generate enough gravity to hold them together. According to the laws of physics, the Coma Cluster should have flung itself apart billions of years ago. Yet there it was, perfectly intact. Zwicky proposed a radical idea. There had to be something else there, something invisible, providing the extra gravitational glue. He called it dunkel materie, or dark matter. For decades, his idea was largely dismissed. But today, it's a cornerstone of modern cosmology. The Coma Cluster was our first real clue that about 85% of all matter in the universe is completely invisible, detectable only through its gravitational pull. Modern observations have confirmed Zwicky's insight in stunning detail. X-ray telescopes show us that the space between the galaxies in Coma isn't empty. It's filled with a seething plasma, a superheated gas that glows at tens of millions of degrees. This gas accounts for more of the cluster's normal matter than the galaxies themselves. But even combined, the galaxies and the gas are just the tip of the iceberg. The true mass, the gravitational backbone holding it all together, is the enormous unseen halo of dark matter. The Coma Cluster taught us a crucial lesson. In the universe, the invisible rules the visible. If the Coma Cluster introduced us to the mystery of dark matter, our next destination provided the smoking gun. Meet the Bullet Cluster, located 3.7 billion light-years away. This isn't just one cluster, it's the spectacular aftermath of a cosmic collision, a smaller galaxy cluster. The Bullet has smashed through a larger one at a mind-boggling speed of over 4,500 kilometers per second. In 2006, astronomers combined data from optical telescopes and NASA's Chandra X-ray Observatory to create a composite image of the event. And what they saw was extraordinary. The hot gas, which makes up most of the normal matter, was seen glowing in pink X-rays. As the two clusters collided, this gas crashed together, slowed down, and created a massive shockwave, much like the sonic boom from a supersonic jet. But here's the critical part. Astronomers also mapped the cluster's total mass by observing how its gravity bends the light from distant background galaxies, a phenomenon called gravitational lensing. They discovered that most of the mass wasn't where the hot gas was. Instead, the bulk of the mass, shown in blue on the images, had passed straight through the collision without slowing down at all, moving right along with the galaxies. This separation was definitive proof. Normal matter, the gas interacts and collides. But most of the mass was made of something that didn't interact. It just sailed through, affected only by gravity. That something is dark matter. The Bullet Cluster became the most direct visual evidence of dark matter's existence. A cosmic experiment that nature performed for us on a galactic scale, writing the laws of physics in the language of a collision. So we know dark matter is real, and it's the dominant source of gravity in clusters. But what does it actually look like? Well, we can't see it, but we can map it. Every galaxy and every galaxy cluster is thought to be embedded in a massive invisible sphere called a dark matter halo. These halos are the true skeletons of the cosmos. They are far larger and more massive than the luminous galaxies they contain. Think of it like this. The galaxies are like Christmas lights strung up on a vast, invisible tree. The tree itself, the structure providing shape and support, is the dark matter halo. Its immense gravity not only holds the cluster together but also warps the fabric of space-time around it. This warping is what causes gravitational lensing, allowing us to map the halo's shape and size. When we study massive clusters like Abell 1689, we see distorted, stretched-out images of galaxies that lie far behind it. The amount of distortion is so extreme that it can only be explained by a colossal amount of mass, far more than we can see. These halos aren't static either. They grow over cosmic time, merging and pulling in smaller structures. This is how the universe builds itself, from the bottom up. Small dark matter halos formed first, attracting gas to form the first galaxies. These then merged to form larger galaxies, which in turn grouped together to create the titanic clusters we see today. Without dark matter halos, the universe as we know it simply wouldn't exist. Now, let's go back to that superheated gas we mentioned, the stuff filling the space between the galaxies. This is called the intracluster medium, or ICM, and it's a hidden reservoir of cosmic history, though invisible to our eyes. This plasma, glowing in X-rays, contains the majority of a cluster's normal baryonic matter. This gas is a record of billions of years of cosmic violence. Every time galaxies merge, every time a star goes supernova, heavy elements are forged and blasted out into this medium. As galaxies fall into the cluster's immense gravitational well, the intense pressure of the ICM can strip them of their own gas, leaving long, beautiful trails behind them. This process, called ram pressure stripping, enriches the ICM and tells us about the dynamic life of galaxies within these dense environments. By studying the temperature and brightness of this X-ray-emitting gas, astronomers can not only understand the cluster's history, but also calculate its total mass. The gas sits within the gravitational valley carved out by the dark matter, and its properties are directly tied to the depth of that valley. This provides yet another independent way to confirm the overwhelming dominance of dark matter. Because they are the biggest and most massive things around, galaxy clusters are more than just objects of study. They are cosmic beacons. Their distribution across the universe isn't random. They trace the largest known structure, the cosmic web. This is a vast network of filaments and voids, formed by gravity acting on tiny fluctuations in the early universe. Clusters form at the intersections of these filaments, like major cities at the junctions of cosmic highways. By mapping the locations of thousands of clusters, surveys like the Sloan Digital Sky Survey have given us an unprecedented view of this grand structure. And the number of clusters we find at different distances, and thus at different times in cosmic history, tells us something fundamental about the universe itself. Their growth is a delicate balance between the pull of gravity and the push of dark energy, the mysterious force causing the universe's expansion to accelerate. By counting clusters, we can measure the strength of dark energy and probe the ultimate fate of our cosmos. From the Coma Cluster, which first hinted at an invisible universe, to the Bullet Cluster, which proved it with a cosmic smash-up, galaxy clusters are the silent giants that define our reality. They are the magnificent end products of 13.8 billion years of gravity at work, pulling matter together, building order from chaos, and shaping visible forms from an invisible blueprint. They remind us that what we see is only a tiny fraction of what truly exists. Within these immense cities of galaxies, we find the story of the universe written on the grandest possible scale, a story of hidden matter, cosmic collisions, and the fundamental forces that govern everything. Have you ever looked up at the night sky and felt a sense of wonder? Well, get ready to feel a sense of profound mystery, because every single galaxy cluster we see, from our neighbor the Coma Cluster to the most distant systems, holds a paradox. They're just too massive. The galaxies inside are moving so fast, the gas is so incredibly hot that by all rights, they should have flown apart billions of years ago. Yet they don't. Something invisible, something vast and silent, is holding them together. This is the mystery of the missing mass, and galaxy clusters are the cosmic crime scene where the evidence is most glaring.
Ow.
This story starts almost a century ago, with an astronomer named Fritz Zwicky. While studying the Coma Cluster, he did the math and came to a shocking conclusion. There had to be 400 times more mass in the cluster than what he could see. 400 times? This wasn't a rounding error. It was a crisis. Either our understanding of gravity was fundamentally wrong on a cosmic scale, or most of the universe was completely invisible. At the time, most people ignored him. But Zwicky had planted a seed that would grow into one of the biggest quests in all of science. Decades later, astronomers like Vera Rubin confirmed the same problem, but inside individual spiral galaxies, they saw that stars on the outer edges were moving just as fast as stars near the center, which made no sense. It was like the outer horses on a merry-go-round moving at the same speed as the inner ones. The only way this could happen is if each galaxy was embedded in a massive, invisible halo. But galaxy clusters take this problem to a whole new level. The missing mass isn't just hiding in dim stars or cold dust. We've looked. It's something else entirely. Something non-luminous. Something that isn't made of the protons and neutrons we're familiar with. We call it dark matter. The leading explanation for this cosmic ghost is dark matter, a strange new kind of substance that doesn't interact with light at all, just sits there, exerting gravity. And the evidence is everywhere. Take gravitational lensing. Massive objects bend space-time, causing light to curve around them like a lens. Galaxy clusters bend light far more than their visible matter can account for. The stunning arcs and distorted images of background galaxies you see in Hubble photos are direct proof of this invisible mass at work. Then there's the scorching hot gas between the galaxies in a cluster. This gas is so hot it emits X-rays, and its temperature tells us exactly how strong the cluster's gravity is. Again, the numbers only add up if there's 5 to 10 times more mass than we can see. Dark matter acts as the gravitational scaffolding of the universe. It pulled in the normal matter after the Big Bang, creating the cosmic web of filaments and clusters we see today. Without dark matter, we simply wouldn't be here. But the billion-dollar question remains, what is it? The hunt for dark matter has led scientists down some fascinating rabbit holes. For a long time, the top suspect was a particle called a WIMP, or a weakly interacting massive particle. These would be heavy particles that barely interact with anything, making them incredibly hard to find. Huge detectors have been built deep underground, shielded from cosmic rays, waiting for the gentle ping of a WIMP bouncing off an atomic nucleus. But after decades of searching, silence, so scientists are now exploring other, more exotic possibilities. What about ECNs? These are ridiculously lightweight particles, proposed to solve a completely different problem in physics, but they might just fit the bill. Or maybe sterile neutrinos, heavier cousins of the neutrinos we already know, which interact only through gravity. Each of these candidates would form the universe in slightly different ways, but so far none have revealed themselves. Of course, there's another more radical idea. What if it's not a new particle? What if gravity's wrong? A theory called MOND, or modified Newtonian dynamics, suggests that gravity itself behaves differently at the very low accelerations found in the outskirts of galaxies. MOND is brilliant at explaining the rotation of individual galaxies without needing dark matter. But when you try to apply it to galaxy clusters, it falls apart. It just can't account for the massive gravitational effects we see there. As of today, dark matter, as strange as it is, remains the simplest and best explanation that fits all the evidence. And the weirdness doesn't stop there. Even when we account for all the normal matter we should see the stuff made of atoms, we come up short. About half of the universe's baryons, the protons and neutrons that make up stars, planets, and us, are missing. Where did they go? Recent observations suggest they might be hiding in a super diffuse hot gas that stretches between galaxy clusters, forming the filaments of the cosmic web. It's so thin, it's almost impossible to see. So, in a strange twist, the normal matter is actually the hardest to find. But galaxy clusters aren't just shaped by what pulls them together. They are also being pulled apart by the most mysterious force in the cosmos, dark energy. This is the force causing the expansion of the universe to accelerate. As space stretches faster and faster, it becomes harder for gravity to pull matter together to form new clusters. The ones that already exist are becoming cosmic fossils, isolated islands in an ever-expanding ocean of space. By studying how the number of clusters has changed over cosmic time, we can actually measure the strength of dark energy and predict the ultimate fate of our universe. Perhaps the most spectacular gift galaxy clusters give us is gravitational lensing. Their immense mass turns them into natural telescopes, magnifying and distorting the light from galaxies lying far behind them. We can see galaxies so distant that their light has traveled for over 13 billion years, giving us a peek into the universe's infancy. Clusters like Pandora's cluster act as a 3D map of dark matter, revealing its complex, clumpy structure. They are not just mysteries. They are tools that help us solve other cosmic puzzles. So, when we add it all up, the universe is a far stranger place than we ever imagined. Only about 5% of it is the normal matter we know and love. 27% is the invisible dark matter holding it all together. And a whopping 68% is the mysterious dark energy pushing it all apart. Galaxy clusters are the one place where all three of these cosmic ingredients meet in a dramatic cosmic dance. They are the grandest experiments in nature, and they hold the key to understanding the fundamental laws of our universe. The equation is unfinished, but the clues are out there, waiting in the silent spaces between the stars. When you look up at the night sky, have you ever felt a sense of wonder? A feeling of being part of something immense and eternal? For thousands of years, that glittering band of stars we call the Milky Way was our universe. It was everything. But today, we know our galaxy is just a single grain of sand on an infinite cosmic shore. It's one of hundreds of billions, all bound together in a magnificent, invisible structure. So, let's take a journey. A journey to find our true address in the cosmos. We all know we live on Earth, which orbits the Sun. Our Sun is just one of 200 billion stars in the Milky Way galaxy. But where does the Milky Way live? Our galaxy isn't alone. It's part of a small cosmic neighborhood called the Local Group, a collection of about 50 galaxies. And this group, in turn, is just a tiny part of something far, far grander. An immense supercluster of galaxies spanning 500 million light-years. Its name is Laniakea, a beautiful Hawaiian word that means immeasurable heaven. This is our home on the grandest scale imaginable. To understand Laniakea, we first have to zoom out and see the universe's architecture. It's not a random scattering of galaxies. It's a cosmic web. Imagine dense knots of galaxies called clusters, connected by long, glowing filaments of gas and stars. In between these filaments are vast, dark chasms called voids, regions of almost complete emptiness. Superclusters are the largest, most massive structures in this web, where countless galaxies are flowing together, pulled by their mutual gravity. Our own Milky Way is located in a relatively quiet suburb of this cosmic metropolis, within the small local group, which includes our famous neighbor, the Andromeda Galaxy, and about 10 million light-years of space. It feels huge, but it's just a drop in the cosmic ocean. For a long time, astronomers thought we were part of something called the Virgo supercluster, because the massive Virgo cluster, about 54 million light-years away, is our closest major cosmic landmark. It's a bustling city of over 1,000 galaxies, and its gravity definitely pulls on us. But in 2014, a team of astronomers led by Brent Tully made a discovery that completely redrew our cosmic map. They didn't just look at where galaxies were. They measured how they were moving. They tracked the peculiar velocities of thousands of galaxies, their motions separate from the expansion of the universe. What they found was breathtaking. They discovered that our local group, the Virgo cluster, and thousands of other galaxies were all flowing together. Not randomly, but along defined pathways, like rivers converging into a single massive basin of attraction. This entire flowing region, home to 100,000 galaxies, is what they named the Laniakea supercluster. It's not just a collection of galaxies. It's a dynamic system defined by a shared gravitational destiny. We are all being pulled toward the same point in space. Our old address in the Virgo supercluster was like knowing your street name, but Laniakea showed us the entire city we belong to. At the very heart of Laniakea, at the bottom of this immense gravitational valley, lies a mystery that astronomers have chased for decades: the Great Attractor. It's a region of space so massive that it's pulling our Milky Way, Andromeda, and entire clusters of galaxies toward it at hundreds of kilometers per second. For a long time, we could unsee what it was because it's hidden behind the dense dust and stars of our own galaxy as planar region called the zone of avoidance. But using infrared and X-ray telescopes that can peer through that dust, astronomers have finally identified the culprit. It's a colossal complex of galaxy clusters, with the Norma cluster at its core, acting as the main gravitational anchor. So while you're sitting there watching this, remember that you, me, and our entire galaxy are hurtling through space at over 2 million kilometers per hour. We are cosmic travelers, swept along in an invisible current of gravity, on a slow, multi-billion-year journey toward the Great Attractor. We are not static observers of the universe. We are active participants, constantly in motion. This incredible journey is our shared reality within the immeasurable heaven of Laniakea. But why does any of this matter for us, here on our little blue planet? Because the structure of the universe, our specific location within it, is deeply connected to our very existence. Think of it as a cosmic Goldilocks zone, but on a mind-boggling scale. If our galaxy had formed in the dense core of a cluster like Virgo or Norma, the intense radiation and frequent gravitational disruptions from nearby galaxies might have made it impossible for stable planetary systems, let alone life, to form. On the other hand, if we were born in one of those vast, empty voids, the building blocks of life, the heavy elements forged in stars, might have been too scarce. Our position is just right. We're in the quiet outskirts of a spiral galaxy, which is in a small, calm group on the edge of a vast supercluster. Not too crowded, not too isolated. This specific cosmic address may be one of the key reasons we're here at all, able to ponder these questions. Laniakea isn't just a location, it's the grand environmental context that allowed a world like Earth to flourish. From our vantage point, the night sky appears calm, a peaceful canvas of distant lights. But the reality is a universe of unimaginable dynamism and scale. Every star, every galaxy, and every cluster is part of this intricate cosmic dance, choreographed by gravity. Knowing about Laniakea gives us a profound sense of perspective. We are not at the center of anything. We are part of a gravitational current in a cosmic river, flowing through a structure so vast it defies comprehension. When we study these colossal structures, we're not just looking at distant objects. We're looking at the architecture that shaped our world and gave rise to us. It connects the largest scales of the universe directly to our own existence. For most of human history, the sky was a simple map, a flat dome of lights wheeling around our world. The stars felt eternal, and the Milky Way was just a faint, misty cloud woven into the fabric of night. But as our eyes grew stronger, peering through ever more powerful telescopes, those clouds dissolved into countless suns. The universe expanded in our minds, not just in size, but in concept. And with that came a slow, staggering realization. The stars are not scattered evenly. They gather, they cluster, they build the very architecture of the cosmos. This is the story of how we discovered the invisible giants of the universe, the galaxy clusters and superclusters that shape everything. It all started with a few fuzzy smudges in the night sky. In the 18th century, astronomers like Charles Messier and William Herschel cataloged hundreds of these faint patches. They called them nebulae, Latin for clouds. Some were indeed clouds of gas, like the Orion Nebula, but others, they would soon learn, were something far grander. Herschel noticed these nebulae weren't randomly placed. They seemed to cluster in certain regions. He was the first to suggest our Milky Way was part of a larger structure, a construction of the heavens. His work sparked a question that would define astronomy for the next century. Were these nebulae inside our galaxy, or were they distant island universes all on their own? The question came to a head in 1920 in what's known as the Great Debate. On one side, astronomer Harlow Shapley argued that the Milky Way was the entire universe, a single, vast galaxy containing all the nebulae. On the other, Heber Curtis proposed that the spiral nebulae were external galaxies, island universes floating far beyond our own. The tiebreaker came just a few years later, thanks to Edwin Hubble. Using the mighty 100-inch Hooker telescope, he spotted special pulsating stars called Kyphids in the Andromeda Nebula. By measuring their brightness, he calculated its distance, over 2 million light-years away. Andromeda wasn't a cloud in our backyard. It was another galaxy entirely. Suddenly, the universe was unimaginably bigger. Galaxies, it turned out, were not alone. Even before Hubble's breakthrough, astronomers noticed that galaxies liked to hang out together. In the 1930s, the brilliant but eccentric astronomer Fritz Zwicky took a closer look at the Coma Cluster, a dense swarm of hundreds of galaxies. He measured how fast they were moving and was completely stunned. The galaxies were zipping around so fast that the gravity from all their visible stars could impossibly hold them together. The cluster should have flown apart millions of years ago, yet there it was, perfectly intact. To solve the puzzle, Zwicky proposed a radical idea. There had to be some kind of invisible mass providing the extra gravity. He called it Dunkel Materie, or dark matter. At the time, most astronomers dismissed the idea, but Zwicky was decades ahead of his time. His strange observation in the Coma Cluster was our first real clue that the universe was hiding most of its mass in plain sight. By the mid-20th century, the hunt was on to map these cosmic gatherings. In 1958, George Abel undertook a massive project, poring over photographic plates from the Palomar Observatory. He meticulously identified and cataloged over 2,700 distinct galaxy clusters. This Abel catalog became a foundational map of the large-scale universe. For the first time, we could see the patterns where clusters were dense and where vast, empty voids opened up. Abel's work wasn't just a list, it was a blueprint. It revealed that clusters themselves weren't the end of the story. They seemed to be grouping together into even grander structures, hinting at a cosmic architecture on a scale no one had ever imagined. Then came the digital revolution. The old photographic plates were replaced by CCD detectors, the same technology in your digital camera, but supersized and supersensitive. This allowed astronomers to not only see fainter galaxies, but also measure their redshift, the stretching of light caused by the universe's expansion. Each redshift gave a precise distance, turning our flat view of the sky into a glorious 3D map. And the picture that emerged was breathtaking. Galaxies weren't just in clusters. They were arranged in immense filaments and walls, stretching across billions of light years, surrounding vast, empty voids. This cosmic web is the true skeleton of the universe, and galaxy clusters are the bright, bustling intersections where the filaments meet. Our own Milky Way is just a tiny speck on one of these filaments, part of the Laniakea supercluster hour cosmic home address. But what we see in visible light is only half the story. When we started looking at galaxy clusters with X-ray telescopes in space, a whole new reality was unveiled. Filling the vast space between the galaxies is a colossal ocean of plasma, a gas so incredibly hot, tens of millions of degrees, that it glows brightly in X-rays. This intracluster medium contains more normal matter than all the stars in the Cluster S galaxies combined. Yet it's completely invisible to our eyes. It's all held together by the immense gravitational pull of the cluster, a pull generated mostly by dark matter. By studying these X-rays, astronomers can weigh the entire cluster and create a map of the invisible dark matter that sculpted it. This led to one of the most powerful proofs for dark matter, the bullet cluster. It's a spectacular collision of two galaxy clusters, where the hot gas and the dark matter have separated, giving us a ghostly image of the invisible substance that holds our universe together. Galaxy clusters are so massive, they literally bend space and time. This effect, predicted by Einstein, is called gravitational lensing. When light from a very distant galaxy passes through a cluster, the cluster's gravity acts like a natural magnifying glass, bending and amplifying the light. Sometimes this creates beautiful arcs and rings of light. Other times it creates multiple images of the same background galaxy. For astronomers, this is an incredible tool. We can use these cosmic telescopes to map the dark matter inside clusters with stunning precision. Even better, we can see galaxies from the dawn of time objects, so far away their faint light would be lost to us otherwise. Telescopes like Hubble and the James Webb Space Telescope use clusters as their own magnifying glasses. Peering back to see what the universe looked like when it was just a fraction of its current age. In the last few decades, we've gained another superpower. We can build our own universes inside supercomputers. Cosmologists can now run simulations that start with the Big Bang and include all the ingredients dark matter, dark energy, and the laws of physics, to watch how the cosmos evolves over 13.8 billion years. And incredibly, these virtual universes look just like the real one. The same cosmic web emerges, with filaments, voids, and clusters forming at the intersections. These simulations allow us to rewind the clock and watch how our own cosmic neighborhood formed. We can test our theories, see what happens when we tweak the laws of nature, and even fast forward to see what the universe might look like billions of years from now. For the first time, we don't just observe the universe, we recreate it. The journey to understand galaxy clusters is a story about perspective. We started as a species looking up at a flat sky of scattered lights. Now we see the grand architecture of the cosmos, woven by gravity across billions of years. The light from these distant clusters carries with it the story of the universe's creation. Each image, each measurement, and each simulation reveals the same profound truth. The universe isn't random, It's a dynamic, interconnected, and beautifully structured place. We've learned to read this cosmic map, but the story isn't over. The universe is still expanding and evolving, and the fate of these cosmic giants is still being written. Have you ever stared into the night sky and wondered where it's all going? We often imagine the universe's end as a poetic fading of stars, a gentle dimming of light, but the physics behind it paints a picture that is both majestic and profoundly lonely. We're going to journey to the far, far future, to explore the final chapter for the largest structures in the cosmos, galaxy clusters. These silent giants, vast cities of thousands of galaxies, hold the key to the ultimate fate of all matter, the secrets of dark energy, a legacy that will outlive every star that has ever shone. To understand their destiny, we have to start with the most groundbreaking discovery of the 20th century. The universe is expanding. Back in 1929, Edwin Hubble realized that galaxies are flying away from us, and the farther they are, the faster they go. It's not that they're moving asterisk through asterisk space, but that space itself is stretching, carrying them along for the ride. For a long time, we thought gravity might eventually win, pulling everything back together in a big crunch. But in 1998, everything changed. Astronomers discovered the expansion isn't slowing down, it's accelerating. The culprit is a mysterious force we now call dark energy. It makes up about 70% of our universe and acts like a cosmic anti-gravity, pushing everything apart. This invisible force is what seals the fate of galaxy clusters. While dark energy dominates the vast emptiness between galaxies, the immense gravity of a cluster is strong enough to hold its member galaxies together. Clusters are the largest objects in the universe that can resist the cosmic push. They are gravitational islands in an ever-expanding ocean. Now, let's fast forward billions of years. As the universe continues to stretch, galaxies that aren't gravitationally bound to us will drift away faster and faster. In about 100 billion years, their light will be stretched so thin, so redshifted, that they will become completely invisible to us. The sky for any future observer within our own cosmic neighborhood will be almost entirely black. No distant galaxies, no faint glow from the Big Bang. Each galaxy cluster will become a lonely archipelago, forever isolated from the rest of the cosmos. Our own local group, containing the Milky Way and Andromeda, will have already merged into one giant elliptical galaxy, a megagalaxy sometimes called Milkomeda, drifting alone in the dark. But even in this isolation, life inside the cluster goes on, at least for a while. Gravity doesn't sleep. Smaller galaxies will continue to collide and merge with larger ones, creating colossal central galaxies that devour their neighbors. We can see this happening right now. The Coma Cluster, for instance, already has two monster galaxies at its core, each one dozens of times the size of our Milky Way. Over trillions of years, these mergers will continue, but star formation will grind to a halt as the gas runs out. The once bright clusters will slowly transform into graveyards of old dead stars. One by one, the last stars, the long-lived red dwarfs, will flicker out. All that will remain are the stellar remnants, white dwarfs, neutron stars, and black holes. This is where the timeline gets truly mind-boggling. Trillions upon trillions of years from now, the clusters will be dark. They will be massive collections of black holes and cold stellar cinders, all held together by the invisible scaffolding of dark matter. Over eons, gravitational interactions will slowly kick most of these objects out into the void, leaving behind only a sparse collection of supermassive black holes at the cluster's core, and even they are not eternal. According to Stephen Hawking, black holes slowly evaporate through a process called Hawking radiation. Over timescales so vast, they defy human comprehension. Even the most massive black holes will radiate away, releasing one final, faint burst of energy into a cold, empty universe. At that point, the galaxy clusters, once the mightiest structures in existence, will have completely dissolved. So how can we possibly know any of this? We use clusters as cosmic time machines. By looking at clusters at different distances, we see them at different ages. Distant clusters look young and chaotic, still forming. Nearby clusters like Virgo or Coma are mature and settled. By comparing them, we piece together their life story and project it into the future. Supercomputer simulations, packed with our best understanding of dark matter and dark energy, confirm this vision. They show a universe where the formation of new structures eventually freezes. Galaxy clusters are the last grand constructions of the cosmos before an eternal stillness sets in. For now, we live in a golden age of cosmology. We can still see the cosmic web, trace the filaments of galaxies connecting clusters, and feel the pull of their gravity. The James Webb Space Telescope is already seeing the baby pictures of the universe's first clusters. Observatories like the Vera C. Rubin will map billions of galaxies, while missions like Euclid and Roman will chart the invisible dark matter that holds it all together. We are witnessing the universe in its prime and through these silent giants. We're learning not just about them, but about the fundamental forces that govern everything. When you think about it, there's a profound beauty here. Galaxy clusters represent a delicate balance between gravity's urge to build and dark energy's push to expand. In studying them, we, a tiny species on a small planet, are able to comprehend structures millions of light years across. We are the universe becoming aware of itself. These silent giants will outlive every star, every planet, and every form of life. They are the ultimate monuments of the cosmos. For a brief, shining moment in cosmic history, we are here to see them, to understand them, and to be awed by their silent, immense, and eternal power. Thanks for joining us on this journey to the end of time. If you found this as fascinating as we do, don't forget to like this video and subscribe for more deep dives into the cosmos. See you next time.